Lesson 7 is going to be talking again about a concept called entropy. And entropy, as we know, is all about disorder. So we're going to be looking at entropy and how it is influenced by a phase change diagram. And we're going to be identifying entropy changes based on a negative or positive value. So entropy, as we know from the previous unit, is a term used to describe the variation of molecules produced in a chemical reaction. High entropy in a chemical or physical reaction creates many moles worth of various products. This is what we view as chaotic in the sense of a particle diagram. When we have a low entropy, that's where we have a chemical or physical reaction that creates less moles of a product, or simply transitions towards the solid phase. We refer to this as simple in the sense of a particle diagram. When we look at this particle diagram, we're noticing that we have 12 particles that are sublimating into a gas. This is going from a very simple to a very chaotic system. On the left-hand side, we're noticing less entropy or less disorder, and on the right-hand side, we're noticing more entropy or more disorder. In this example, we're going from, again, a solid on the left-hand side, and it is being dissolved by water, which is being represented by the red and 2 white circles. This phase change, dissolving, is going to be more chaotic. As you're noticing on the left-hand side, you have less entropy because you're being very organized. You're very tightly packed and you're not moving. There's very little interactions. But as that sample was dissolved in the water, now we have all 12 particles being surrounded by these water molecules. Because of the variation in your sample now, you're going to be more chaotic. And you also have way more interactions than before. So let's look at our sample. In the beaker on the left, we have a solid, in the beaker in the middle, a liquid, and in the beaker on the right, a gas. As you go from a solid to a liquid and a gas, you'll notice that on the left, you have the least amount of entropy. This means that you have the most organized sample. As you increase entropy, your particle will break apart and become a liquid. And as you increase it to the greatest amount, your particle will now start to float and disperse itself in a 3D space. Now let's talk about intermolecular forces. Looking on the left, we have our solids. Because of the fact the solids are all clumped together and they're not breaking apart, we can say they have the strongest intermolecular forces. Because the liquid is dispersed throughout the bottom of the container, it has moderate intermolecular forces. And because our gases is floating throughout a 3D space all over the container, we can say it has the weakest intermolecular force. And finally, let's understand what the different values of entropy mean. As you go from a solid to a liquid to a gas, we're going to say that you are increasing a change in entropy. And a change in entropy that is increasing as you go from ordered to disordered is a positive delta S. The S symbol represents entropy. However, if you do the reverse, as you go from a gas to a liquid to a solid, as you go from a very chaotic system into something that's incredibly organized, you're going to be losing entropy, which we're going to be representing as a negative delta S, or a negative change in entropy. So positive entropy, which is represented by a positive delta S, means that your entropy has increased. This means that your products are going to be more disordered. For example, that means when carbon dioxide solid sublimates into carbon dioxide gas, you are going to be increasing entropy. Entropy increases if more moles are also being formed. If you looked on the left side of the first equation of mercury oxide, you only have 2 moles of it. But on the right-hand side, when they decompose, you have 2 moles of mercury and 1 mole of oxygen. Thus, you have a 2 to 3 mole ratio. You have more moles as a product. Same thing goes for the 2 moles of ammonium. When the 2 moles of ammonium break apart into 1 mole of nitrogen and 3 moles of hydrogen, you have 2 moles to 4 moles. You have 4 moles as a product, which is more than what you started with. However, some ways to decrease entropy are represented by a negative delta S. This means that your products are going to be more organized. This means, for example, as iodine deposits itself as a gas into a solid, its particles are rearranging themselves back into a crystal lattice structure. All types of chemical or physical reactions with a positive delta S or are exothermic, things that give off heat, tend to be spontaneous. So let's look at some of these practice problems on entropy and phase changes. As solid ice gains energy, it phase changes into gaseous water. That means we have an increase in entropy, which is a positive delta S. Next up, we have C2H4 gas, and it turns into C2H4 liquid and energy. So this means we're going from a gas to a liquid phase. That's going to be a decrease in entropy, just because of the fact we're going from gases to liquids. Next up, we have calcium carbonate liquid, and it's turning into calcium carbonate solid. This means when you're going from a liquid to a solid, you're cooling down the sample, which is bringing the particles back together. That means you're also decreasing in entropy. Finally, liquid bromine is turning into gaseous bromine. Because you're going from a liquid to a gas, we're going to be increasing the entropy. So let's look at this problem right out of the Regents. Given the balanced equation of KNO3 plus 34.89 kilojoules of energy, which is being dissolved in water, making potassium ions and nitrate ions, which statement best describes this process? Well, before I even look at the possible answers, let me just analyze what's going on. I'm noticing that a solid sample is being dissolved in water. A solid sample being dissolved in water means that that solid is now being broken now into ions, which we see as our products. Because the solid sample's ions are floating in an aqueous solution, no longer confined to the bonds of a crystal, a solid, that means they're going to be spread out and they're going to be constantly moving, just like a liquid. That means that the phase change that we're seeing is a solid to a liquid. We're also noticing that heat is a reactant, which means that it's endothermic. Heat is entering the system to help the potassium nitrate dissolve in the water. Therefore, which statement best describes this process? Well, if we look at it, we understand that entropy is increasing and energy is being absorbed. This means that the answer should be 1. It's an endothermic reaction and entropy is increasing. Now let's try 4 more practice problems. Well, we're starting off with a solid sample of potassium chlorate, and it's decomposing to make solid potassium chloride and gaseous chlorine. This is going to be an increase in entropy because the solid reactant is forming 2 moles of product. It's also forming from a solid a gas product. In the second sample, you have carbon dioxide gas plus water gas, and it's going to give you sugar, which is a solid, and oxygen, which is a gas. In this situation, you're not changing the amount of moles, even though the chemical formula is not balanced. If you look at this problem carefully, you'll also notice that your 2 reactants are gases, and they're making 2 products, one of which is a solid. Because your gas reactants are forming a solid product, we can state that entropy is decreasing. In the third example, you have nitrogen gas plus 3 moles of hydrogen gas, and they're giving you 2 moles of ammonium gas. Here we have a gas plus a gas making a gas. But when we look at the amount of moles on our reactant side, we have 4 moles total. 1 mole of nitrogen, 3 moles of hydrogen. There we have 4 moles, and we only have 2 moles of product. So we're actually decreasing the amount of product, so that's a decrease in entropy. There are going to be less particles now bouncing around a given space. And finally, we have carbon dioxide solid, and it is going to be reacting with oxygen. This then undergoes a reaction to make carbon dioxide gas. This is going to be an increase in entropy because the solid is going to be turning itself into a gas. So finally, if we look at this little diagram, we can understand the fact that as we increase enthalpy, which is the overall change in heat of a solid, we're going to be going up in a phase change. As we do that, we have to undergo the heat of fusion. Once we have the heat of fusion, we will then become a liquid. Once we undergo the heat of vaporization, we become a gas. Once we get to the gas phase, if we want to decrease our enthalpy to return back to the solid state, we have to undergo the condensation and freezing phase change. As we do this, the amount of entropy also increases and decreases. From a solid to a gas, it increases. But as a gas turns back into a solid, it will be decreasing.